All right, we're on to this page here, and we've got this graph, and we're told that this is a graph of g of x, and then we have a position function given to us that says the position of a particle is the integral of this function from 0 to t. Now, what that means then, if we kind of do this up here, is that if I took the derivative of the position function, which would give me velocity, it would be the derivative of this integral. And when you take the derivative of an integral, you're going to cancel it, and it means that this g of t, so this graph that you're looking at, represents the velocity of our particle. So I'm going to actually write that here, that this g function also acts as a velocity. Why again? Because the position is the integral of this. Therefore, if I take the derivative of position, which gives me velocity, I take the derivative of an integral, cancels it, leaves me with that. That means the acceleration then would be the derivative of this function here, but we'll deal with that later. What is the particle's velocity? Well, this is the velocity function, and at 3, the velocity is 0. Okay. Is the acceleration at t equal 3 positive or negative? Since the derivative of velocity is acceleration, and this is increasing at 3, we would say that acceleration is positive. Velocity is increasing. What is the particle's position at 3? Well, position function was given to us here. S of 3 would be the integral from 0 to 3 of g of x dx. In other words, the area of the velocity graph would give us the position at 3 seconds. So if I do the area of this, 1/2 3 times 6 is 9. It's negative. So we would say the particle's position is a negative 9. Okay? 9 to the left of wherever we're at. When does the particle pass through the origin? So now, initially at 0 seconds, we were at a position of 0. So we start at the origin and we head to the left. Our velocity is negative. So we're moving to the left for those 3 seconds. All right, we get to negative 9, and then we turn around and we start heading to the right. We have a positive velocity after that. So from then on, we're moving to the right. But the question is, when do we hit that origin again? So if we were at a negative 9 here, we need to go 9 more spaces before we hit the origin again. And that would be at t equals 6. So again, the idea being we start at the origin, we head to the left, we move 9 spaces to the left. That's what this area tells us. We change directions at 3, because we switch from a negative velocity to a positive velocity. And then we head 9 spaces again. We hit the origin at t equals 6. Now we continue moving to the right after that, and that'll come up in a problem here in just a second. When's the acceleration 0? Again, acceleration is our derivative here. So when do we have a derivative of 0? And that would be at t equals 7. When is the particle moving away from the origin? So initially we start at the origin, we move to the left. So we are moving away from the origin from 0 to 3 seconds. Now at 3 seconds, we turn around and we start heading back towards the origin. We're still in the negative area, but we're heading to the origin. We hit the origin at 6 seconds. Okay, so we're moving away from the origin from 0 to 3. From 3 to 6, we're moving toward the origin. And then we hit the origin at 6 seconds. Okay, now after that, we keep moving to the right. So from 6 until the very end of this, and we'll say 10 seconds here, from 6 to 10, we're moving away from the origin again. We're moving in the positive direction. So this was moving in the negative direction, in the negative area, away from it, turn around. Now we're moving toward the origin, but we're in the negative area. We hit the origin at 6, and then we're moving in a positive direction in the positive area away from it. So on which side of the origin are we at t equal 9? We are to the right. We're in the positive area. We're in a positive position to the right of the origin. Okay. Down here, we're given a graph. We're told g of x is the integral of this function from 1 to x. That means we can write, it's always a good idea to write it out right away, that the derivative of g would be the derivative of this integral, which cancels it, which means this function here will be the derivative of this function g. Now, when I want to find actual values, then g of 1, I'm just going to put 1 in for x. It's the integral from 1 to 1 of f, which would be 0. G of 3 would be the area from 1 to 3 of f. So the area from 1 to 3 is this triangle here. It's got a height of 1, a base of 2. 2 times 1 divided by 2 is 1. It's in below the x-axis, so that would be a -1. G of -1, same idea. We're going to go from 1 to -1. So from 1 to -1 would be this quarter circle. It has a radius of 2. So pi times 2 squared is 4 pi. I just want a quarter of it. So that would be pi. But I did go in the negative x direction to get there. So it'll be a -1 then. Find all the values of x on the open interval -3 to 4 in which g has a relative maximum. G will have a relative maximum when g prime, which is f, this function, switches from positive to negative. And that switch from positive to negative happens at t equal 1. Right, equation for the line tangent to the graph of g at x equal 1. So anytime I see a tangent line, I need a point and I need a slope. Now the point, the x coordinate is -1, but if you come back here, we know the y value is -1 as well. We already figured that out on part C. As far as the slope goes, g prime is this function, right? At -1, this function is at a height of 2. So that's the slope. So y minus -1 or y plus 1 equals slope times x minus -1 or plus 1. And there'd be our tangent line. Okay. And then F says find the x coordinate for each point of inflection. Now, a point of inflection is when your original function changes concavity, but that's not going to be easy to see because what we have is the derivative. So now when our derivative is increasing, my function, my original function, will be concave up. When the derivative is decreasing, the original function is concave down. So we have a switch from increasing to decreasing at -1. All right? And then later on, you see we have another switch from decreasing to increasing at +2. So those are our 2 points of inflection.